Thank you all for coming. My name is Max. I've been working on search at Airbnb for about 2.5 years. Previously, I was at Google where I worked on search relevance. This talk will be about search architecture at Airbnb, specifically how we leverage Lucene as one of the core components of our search infrastructure, while also building out many custom components on top of it to adapt the search system to our needs. First, I just wanted to give a bit of context for people who may not be familiar with Airbnb and what we do. So Airbnb is an online marketplace for unique accommodations. Essentially, we provide a platform for our hosts to list and manage their properties, including the availability, pricing, incoming inquiries, and so on. We also provide a trust layer, and we handle all payments through our transaction system. By lowering the entry barrier to participate in this accommodation market, we have collected a large and diversity of listings from around the world. This includes everything from spare bedrooms in private homes to entire villas or even private islands. And by matching these listings with an audience of millions, we provide our hosts with an easy way to monetize the extra space and also meet travelers from all around the world. And one of the key components of Airbnb is a search engine that enables our users to discover listings matching their taste and preferences. It processes close to 1 million active listings we have today on the platform, checking them against a complex set of conditions, including calendar availability and geographic positioning. It also calculates ranking scores, which are composed of hundreds of signals for each listing. To do all this, we built a highly customized search system on top of Lucene that we're going to discuss in this talk. First, I want to touch on a technical stack at very high level. Search is implemented as a Java service on top of the Drop-Wizard framework. We use Google's Juice framework for dependency injection. We use Zookeeper for service discovery. It is actually coupled with SmartStack, which is our wrapper around it that implements common service discovery and registration patterns. We actually open sourced it earlier this year. We use Lucene as an index storage and retrieval engine, and we have a lot of custom code that implements the functionality we need, including our ranking and real-time indexing systems. And search interacts with the primary web application that actually implements the user interface via a simple JSON via HTTP API. So search is a multi-threaded server. In addition to all the search threads, which process incoming requests in parallel, we also run 4 dedicated threads that are responsible for maintaining an up-to-date representation of all the data we care about internally. This includes the Lucene index, a separate forward index for ranking signals, and all the relevance models. So Lucene indexes all the information that is essential for retrieval and needs to be updated in real time. This includes various categorical and numerical properties of listings, like the room type and the maximum occupancy of each place. It includes calendar availability information. It indexes the text of description and reviews, as well as geographic placement of listings. For geo, we use the recursive prefix tree strategy from Lucene, which allows us for efficient retrieval using various shapes like polygons or circles. Most of this data comes from MySQL, which is updated by the web application that users interact with. And in total, we have about 40 fields for each listing that are composed from data from a variety of different tables across multiple physical databases. There are a couple of challenges here. So the first one is, how can we bootstrap the index from scratch? Maybe the index format changed, which sometimes happens with new releases of Lucene. Or maybe we simply want to spin up a few new instances of search. Simply streaming data from MySQL is a very slow process, since the data is pieced together from a variety of different sources. The other challenge is, how can we keep the index on all search machines consistent with the ground truth data in MySQL in close to real time? If, for example, someone booked a listing and it is no longer available for a certain set of days, we don't want to keep showing it in search results. One approach is to have the application proactively notify search indexers about any changes it's making. And this is actually what we used to do in the past, but we found this approach to be quite error-prone because in an application as big as ours, there are just too many ways the underlying data can be modified, and it's really hard to track all the changes. So our indexing architecture diagram looks like this, and we're actually going to focus on the upper part first. So there is a number of MySQL databases that store the ground truth information about Airbnb listings. And Spinal Tap is our service that knows what kind of data services like search care about and how to detect changes that happen to it. Its implementation is based on a feature provided by recent versions of MySQL, which is binary log streaming. Spinal Tap tails binary logs from several MySQL servers, which contain a record of all the changes that happen to the data. It converts them to actionable data object called mutations and broadcasts them to subscribers using a distributed queue like Kafka. One of the core concepts of Spinal Tap is a pipe, which represents a channel which has one or more binlog sources, typically MySQL servers, and one destination like Kafka. Pipes are configurable, so different consumers can create their own pipes using different combinations of sources and destinations. So here's an example of pipe configuration in YAML format. So Spinal Tap parses the binlog events and converts them into one of the following mutation objects. It can be either insert, delete, or update. An example mutation in JSON format is on the slide. Insert and delete mutations have the entire row which was inserted or deleted, while the update mutations have both the old and the current row. So for this example, we have an update mutation where we change the age of the user. Spinal Tap also adds more information to each mutation object that is not present in the original binlog. For example, the unique ID, sequence number, and column and table metadata. So now that we can detect data mutations straight from the databases, we have to transform them to the appropriate Lucene indexing events. This presents some challenges. Each document in our index contains data from about 15 different source tables. To index a document, Lucene needs a copy of all fields, not just the fields that changed. And we don't want each search node to issue SQL queries to get all required data, since that presents a scalability challenge. We also need an efficient way to construct a new Lucene index from scratch without putting too much strain on the source DBs. And to solve those problems, we developed the Medusa service. Medusa provides intermediate content store for search objects. It can perform full data reads to bootstrap itself and get real-time data updates from sources like Spinal Tap. The data from multiple different MySQL tables is merged together into thrift objects, which correspond to Lucene documents. These thrift objects are persisted in a key value store that is owned by Medusa. As it gets notified about the changes by Spinal Tap, updated objects are pushed to the search instances to perform modifications of the local Lucene indices. Search instances can also request individual objects proactively, or even request a scan of the full index if required. In a multi-threaded mode, the entire Lucene index can be reconstructed from Medusa in about 3 minutes. And there are multiple Medusa instances in production. One serves as the leader and is responsible for writing updates to Redis, while every other instance provides data reads. And we use Zookeeper for leader election. So whenever a leader fails, we can always fail over and elect another leader. The next problem is ranking. Lucene's built-in relevance implementation is mostly designed for scoring of text documents against text queries. At Airbnb, while we do support a text-based search feature, it's really not the primary way users are looking for accommodations. The query is usually just a location string that needs to be geocoded to understand its meaning, or a bounding box when users are searching by kind of moving the map around. The query may also contain a number of optional filters as well, such as dates of the trip, the number of guests, price filter, or text keywords. Finally, you can consider the user itself as a part of the query too, because different people can have different implicit preferences about the types of accommodations they like. We can have different budgets in mind. We can prefer different types of accommodations. Maybe someone is only looking for entire homes or like certain kinds of locations. We can infer that from our personalization service that keeps the history of previous actions by the same user. The important thing is the quality and relevance of results we display has a big effect on conversion from search to booking. So there is this constant drive within Airbnb to improve the ranking models and test them out on slices of production traffic through online experiments. One key insight for us is that search is a part of the bigger conversion flow. And the order in which we present the results has a large influence on the hosts that are getting contacts. The hosts on Airbnb are active participants in transactions and can really reject any inquiry for any reason. That's why our ranking problem actually goes beyond just providing relevant results for the user, because we also want to maximize the likelihood that the guest will get accepted if they issue an inquiry to a certain property. So we have machine learning models that, for example, attempt to model the host behavior and try to understand for a given guest and a given trip and the current state of that listing and the host and time of day and the state of the calendar, given all the context, how likely is it that the host will make a positive decision in this case? So here are some high-level components of the ranking score. It includes things like relevance, which is just, is the listing located in a place that's relevant to the user's query? Quality of the listing, so just how desirable the listing is. Bookability, which is the predicted likelihood that the host is going to accept the guest for the requested trip if they make an inquiry. Personalization, again, people may have different budgets, preferences on the types of accommodation, social connections, and so on. Desirability of listings neighborhood, which is based on scores of nearby listings as well. Image content analysis, so we actually have a pipeline which extracts visual features from listing images and tries to predict which images the users are going to like. There is also features like a special promotion for new hosts to help them get started on the platform and get some business initially. So we need a flexible ranking framework to support these requirements. So ranking at Airbnb is a pretty big topic, so I'm not going to go into the details behind like every specific ranking signal in the model, focusing instead just on the infrastructural aspects. So we have several hundred signals that determine search ranking. They are computed offline and loaded into search, and then combined into the final scores at runtime, giving us flexibility to tune the ranking function, run experiments with different parameters for different users, as well as implement query-dependent features, so crosses between like user features and query features against listing features and market features. Many of these signals are computed from very large data sets and rely on complex machine learning pipelines. So we use Hadoop and Spark as our tools for offline data crunching to prepare them in a usable format for loading into the search backends. The final objects are stored in S3 where they become accessible to search. Same goes for machine learning models. They are used to calculate scores during the query time. We train them offline using all available data, including search logs, all the user activity on the core funnel, so we know once you click on the listing, what is the next action that you do, how much time do you spend there, do you contact, if you do contact, are you actually successful in booking, and so In the past, we actually used to commit this data into the Lucene index and then rely on field caches and doc values to retrieve them during scoring. Now we actually just keep them in a separate forward index data structure, which allows us to very easily load another copy of search signals and swap them with existing data at runtime without having to reconstruct the Lucene index, which is still a relatively costly operation. This works pretty well because ranking data is updated in bulk, unlike retrieval data, and it greatly simplifies the design. Of course, this creates some limitations as well. So for example, we can't issue Lucene queries against those fields. So this diagram represents the life of a query inside of the search service. The first stage is understanding the query and appropriately configuring ranking and retrieval parameters. This includes figuring out which ranking experiments should be enabled for the current user, which relevance models to use for that specific class of a query, and so on. Next step is retrieval, which is coupled with the first stage of ranking. We have a custom implementation of Lucene's collector interface that receives each hit from Lucene's index searcher and calls our populator class. The populator class is responsible for creating an object that is going to carry all of listings, ranking signals, intermediate scores, and debug information that we create for engineers, and populates it with the initial set of listings. And once we have a document that is ready for scoring and prepared by the populator, we run all of the lightweight first-pass models, like quality, bookability, and relevance. Depending on the results of this, we can either put the document into a priority queue keyed on the combined score, or we can even decide to throw out the result completely. For example, we may choose not to display a listing which has a very low predicted likelihood of acceptance, even if it's of a reasonable quality and relevance, because it's basically a trap for the user. So once we have a smaller set of 2,000 best results that we have seen so far, we perform another pass of ranking and filtering. For example, we can't afford to call the external pricing service to calculate the accurate prices for every listing on like 1 million of objects. That would just be too slow. So we do this now on this reduced set of 2,000 best listings we've seen so far. And then we use that information for price-based ranking and for price filtering and so on. Same goes for social connections, where we call an external service to basically find the intersection between the set of results and the second-degree social connections of the user, again, to perform additional filtering and personalization. There are also some ranking features that are not possible to implement in the traditional scoring framework, even if we disregard performance considerations. But that are possible on the second pass. An example of that is really anything that has to depend on the context. So traditionally, the scoring functions operate on a single document at a time, right? So it's basically a function of a query and the features of a document, and the function computes a score, and in the end, we simply either sort by those scores or we use that score to put the document into a priority queue, which maintains the current set of results. So when we rank each document DI here, we don't have any knowledge about any other results that are going to stand next to it in the list. And this makes it impossible to implement features like enforcing diversity of results. Let's say we want to show listings at different price points, room types, locations, or maybe we want to make sure that a single person, a single host, if they have multiple listings, can't actually occupy multiple positions on the same result page. Second pass ranking circumvents all of this by operating on the entire list at once. The list it accepts is already pre-ranked by the first pass scorers, so all it needs is to do modifications that it's actually designed for. And we have multiple second pass rankers that run in order. There is also a third pass ranking stage, which operates only on the top 25 results. This is where we can run like the most sophisticated and computationally expensive algorithms, like large random forests and so on. The important thing here is that the listing object, which was created by the populator originally and then filled with information by all the ranking models, is further extended and then logged to Air Events, which is Airbnb's logging system. This allows us to, in the future, go back, look at the logs, see all the values that every ranking signal had at the time of the query, and all the subsequent user activity, like given an impression, did the user actually click on that result? Did they inquire? If they inquired, did they book? And we can use the data as essentially training examples for our machine learning model. So there is this constant feedback loop. This information is also available in our evaluation tools, where engineers can look at the debug output generated by search system to explain why results are ranked in a certain way. This particular tool allows us to create comparison sets between different ranking functions, or simply different versions of the same code base. An engineer can specify which backends to scrape and tune all kinds of parameters. And then the tool issues queries from a sample of real user activity and detects which queries produce different results under those different options. And as a result, it creates this report that you can see on the right side, which includes some summary statistics. So the change rate by different change thresholds. We actually compute Kendall-Stowe rank correlation on the result set to figure out how different ranking is. The intuition is if you have the results being swapped at the bottom of the list, it's less important than the results being swapped on top, and so on. So you can see if you care about a certain threshold of changes, this is how many queries are affected from a random uniform sample. You can also see the impact on the distribution of prices we show at each position on the page. And you can see the distribution of room types we show, so how many entire homes, private rooms, shared rooms, and so on. And most importantly, it also contains a set of examples ranked by the change rate. So you can actually dig into them in a side-by-side view. So this is useful both for ranking engineers who need to ensure that their ranking change does what they actually think it does, and the infrastructure engineers as well to make sure that their changes are ranking neutral. For example, we originally used this tool when upgrading to Lucene 4 to make sure that the new version of the code base produces the same results as the old one. So here you can see on the left side, you can see the baseline, and on the right side, you can see the test. And then for each listing, you can see its location, the number of reviews, its average review score. Most importantly, you can see where that result lies on the other side. So you can see that, for example, the first result on the left side got demoted to position 23 on the right side. And you can also open the debug output, which allows you to see all the underlying signals and scores to understand why a result is ranked in a certain way. I had to blur this out, unfortunately, to make sure we don't disclose private information about the performance of that listing. So we found this tool to be very helpful for rapid iteration because the actual A/B test can take up to a month to run to get statistical significance. But this allows you to very quickly get a sense on what kind of change, what kind of effect can your change actually have on ranking. And of course, the ground truth for any kind of final launch decision is a controlled experiment. We don't launch any ranking changes without A/B testing them on production traffic first. And so ranking change can be deployed to a percentage of users, and then we can observe their behavior on the conversion flow. We can see how the treatment differs from control. So for example, you can see contact to book, search with dates to bookers, and so on. And you can also see the statistical significance of a change in any of these variables. So this is a screenshot of our A/B testing tool that's called ERF. Right. So Thanks, everyone. If you have any questions, feel free to ask. We have a few minutes left. Sure, go ahead. Mhm.
What kind of?
So it's based on explanations. So it reuses the same explanation class that we have, which outputs HTML. But we fill out that explanation content with um, our own output. It includes both the initial signals that were loaded from S3, as well as all the intermediate scores computed by each model.
Can you talk a little bit more about the forward index of ranking signals and the custom collector? Does the custom collector retrieve the ranking signals for every hit, or just the hits that are left in the priority queue when you're done?
So before it even hits the priority queue, it actually retrieves a subset of ranking signals that we use on the first pass of scoring and performs the initial score computation. That way we can figure out if this document should even belong to the priority queue, right? So if the priority queue is already filled up, we can compute the score and we can see that maybe the score is actually worse than the last listing in that queue. Or maybe we can decide to just filter out if, let's say, bookability prediction is just too low. It's basically an in-memory map.
I have a question about the second and third pass ranking.
Mm-hmm.
Can you go a little bit more in depth about what the differences are between your second and third? Because obviously your third is only working on 25 results. So what computationally intensive things are you doing that have to be done on such a small set? And potentially what are your ranking models that you're using?
Yeah, so we use several different kind of machine learning algorithms. We have very lightweight linear regression-based models that we can use on the first pass. We also have large-scale random forests, which we can use on the second pass. Those models are typically very big, and they also contain a lot of branching. So whenever you run a model, there is a lot of cache misses that happen, which has a performance impact. So you can't really score like a million of document using such a model. We also have large-scale linear models that we use, for example, for image content ranking. And those models can have potentially tens of thousands of features as well. So even generating those features takes up significant computational resources.
Hi, I'm wondering, do you use the Lucene boost queries and boost functions at all, or do you just rank using like in code?
So we rank using our custom code. And the primary reason is we actually want to have the maximum flexibility, and we want to be able to modify the ranking factors for every user.
Okay, so would it be possible that the actual better result is beyond that 2,000 results? Like maybe the 2001st result is actually more relevant. Like, was that ever a problem?
I think it is possible. Of course, by definition, first pass ranking is approximate. But usually that doesn't present a big problem in practice. Once the users introduce a lot of filters, so if you look at the search activity, sometimes people issue like very broad queries. So for example, someone might be searching for Europe, and you might have like 500,000 listings just in Europe. And obviously, as we apply the first pass, most of the results get filtered out at that point, right? But the other side of this is for queries as broad as this, they're typically very exploratory queries, so they don't convert anyway. Really, what we want to do here is we want to show the users a diversity of where we have listings, the fact that we have Airbnb listings in every major European city. And then they can narrow down the query, narrow down the location, apply all kind of filters, and then typically we deal with a smaller set of results.
Hi, I'm just wondering, in Medusa, when you get updates from Spinal Tap, if you have updates that don't contain, say, your primary listing ID, like how do you update those? How are you able to identify those records and make those partial updates? Or do you always have identifying information with every associated table?
So the way our data models are designed, you can actually do this. Sorry, my presentation is out. Because for every row that we care about, there is actually either a listing ID or a user ID, and then we can use that to find the appropriate listings that we need to update in our ready store. Right, I think we are out of time. Thank you all.